Okay, so let's continue. What we've done in the previous segment is obtain the integral form of our first law of thermodynamics. Observe that it is a more general version of the balance of energy. Okay, because as we said at the end of that last segment, and as we have here written up on this slide, we have the rate of change of energy, okay, driven by work and heat. All right, so we also can call this an extended version of balance of energy. And when we say extended, we mean that it's extended from the purely mechanical version that we saw in the lectures leading up to this point. Okay, so let's go on and work with this. What we want to do is, as we've done for our other balance laws, move away from this integral form to a pointwise form, right? We want to get at a PDE. Okay, and the way we do that is continuing to look at this equation that we have up here. This term, if you look at it carefully, is in a form that is ripe for the application of the Reynolds transport theorem, okay? Because we have ddt of some quantity over the current configuration, integrated over the current configuration, and very nicely we have the mass density showing up there. We know how to treat that term. And then we have to do something with the boundary terms here. And as we've done before, what we should observe is that that boundary term is ready for the application of the Gauss divergence theorem. Okay, so let's get to work with that. So, so what we're trying to do is convert the integral form to a local or pointwise form. Okay, so to do this, we apply the Reynolds transport theorem. We apply the Reynolds transport theorem to the left-hand side. And we apply the Gauss divergence theorem to the surface integral term. On doing this, if you look into your notes at what you have on the left-hand side, we get integral over omega t 1/2 rho times the material time derivative of the Euclidean norm of the velocity square. Okay? And for the sake of brevity, I'm going to use this notation for the material time derivative. The same thing happens to the next term. The mass density remains unaffected, and we have the material time derivative of the internal energy per unit mass. These terms integrated over dV equal integral over omega t. We have the working of the body force, the rate of working of the body force, and the local heating unchanged. When you apply the divergence theorem to the two terms that we have on the boundary, we get the following. We get divergence of V dotted with sigma, right? The reason we get the divergence of V dotted with sigma is because if you look at the traction term, that can be written as V dotted with sigma, which gives you a vector, the whole thing dotted with n. Okay, so that's how we're applying the divergence theorem. And then for the second term, which was just minus q dot n, the divergence theorem very nicely works out to be just minus divergence of q. dV. All right. I should mention that what we did for this term is exactly what we did when we studied the balance of energy in a purely mechanical context. So that should be nothing new to you. This term, of course, is straightforward. It is just a classical application of the divergence theorem. Okay? All right. Just a little more work to do on the right-hand side. We need to write out one of those divergence terms a little differently, which we will do right now. The first two terms stay the same. Now, the divergence of V dot sigma gives us two terms. One of those terms is V dotted with divergence sigma. And what is happening here is that we are applying the product rule of differentiation. The next term is spatial gradient of V contracted with sigma. The last term then is the same, minus divergence of Q, minus divergence of the heat flux vector. All this d little v. Once again, I encourage you to go back and look at your notes or look at the unit in which we considered first the balance of energy. We got exactly that set of two terms from here. Okay? We could go, you could very well also go into coordinate notation to work this out in greater detail, right? By now, however, you're probably expert at this, so I will leave that to you to work out. Okay, now if we look at things, we should observe certain interesting things. Oh, wait a minute, I realized that there's one more thing I need to do on the left-hand side here. It's a good thing that I have room. What I'm going to do is apply ddt to v square. When we do that, we get integral over omega t, rho. The half and 2 get cancelled out, but let me write that out here. Okay, chain rule. Okay, now let me point out something to you. If you look at that term, I'm going to label it 1. You look at that term 2, and I look at this term 3. You look at them carefully, and what you should see is that we can pull those 3 terms into the same integral. Okay, and I'm going to do that as the very first thing here. We have integral over omega t. We have rho dv dt, material time derivative of a spatial quantity, minus Bf minus divergence of sigma. All of that dotted with the velocity v dv. Okay? The remaining terms then in our balance of energy are integral over omega t, rho, material derivative of the internal energy per unit mass, dv, equals, on the right hand side, integral over omega t, the local heating, plus the terms that remain there. I'll write this as sigma contracted with the spatial velocity gradient. Okay, minus divergence of q. Right. Now I would like you to stare at this equation. In particular, look at the very first integral on the left-hand side, the volume integral. What do you see written in the parentheses there? What can you say about that term? That term is our balance of linear momentum in the current configuration. Okay? So it is equal to 0, right? Because we assume that the balance of linear momentum is satisfied. Also, we know that sigma is symmetric. Okay? As a result, that term becomes sigma contracted with the symmetric part of the spatial velocity gradient. But that is what we've been writing as d, the rate of deformation tensor. Right? So this is symmetric part of the velocity gradient tensor. All right. So the reason this drops away is, let me put it here, balance of linear momentum. Okay. So when we put these things together, what we see is that we have now, for our first law of thermodynamics in a thermomechanical setting, what we see is that the rate of change of internal energy equals it equals the rate of heating, right, of local heating, minus the divergence of the heat flux plus the work done by the stresses, right? And this is the term that the rate of working done by the rate of working of the stress. And this last term is what we had originally called as the internal stress power. Okay? All right. Now we have our same old argument about localization, right? If this is the current configuration, we could have gone through all of these arguments for any subset. Okay? So this holds for all omega t tilde subset of omega t. Okay? And since I'm saying it holds for all omega t tilde, I should make that domain of integration omega t tilde. Okay? We've gone before through this sort of argument. The only way that can hold is if those integrands vanish, right? Or the integrands are equal. So we see that the local pointwise form of our first law of thermodynamics or the balance of energy for thermomechanical systems is this. Okay, so once again we have rate of change of energy. Here we have heating, and here we have mechanical work rate, right, which is the internal stress power. All right. So once again, you have your first law of thermodynamics in a recognizable form. Okay. One important thing to note here is that we do indeed have the material time derivative here. Right, which is basically dE bar dt equals that partial time derivative plus spatial gradient of E bar dotted with the velocity. Right, that's what's implied there. Okay, that's because E bar is a spatial object. Okay, good place to stop this segment.